by welcoming you here to the Technical Forum at the group exhibit Hydrogen and Fuel Cells 2013. We invite you to have a seat, to have a free drink. Come and enjoy with us the next presentation by the Center of Solar Energy and Hydrogen Research with the topic Advanced Diagnosis Techniques for Water Inventory for Gas Diffusion Layers and Flowfields at ZSW by the research scientist Merle Klages. Give her a big hand, please.
Yeah, welcome to my topic. As mentioned before, it's about diagnosis of water in fuel cells. I'm pleased to see so many people in here. Maybe some of you know about fuel cells, how a fuel cell looks like. If you would cut this fuel cell, if you cut right through, you would see this picture with the bipolar plate, the GDL, the reaction layer, and the reaction itself. The basic reaction of a fuel cell is between hydrogen and oxygen, and it creates water. Water inside a fuel cell is quite important. Where can water occur? It can either occur inside the channels through humidifying the gases or by the reaction. Otherwise, in addition, the water moves through the fuel cell between anode and cathode. Why is water in the fuel cell important? Why to look at water? Water is really important for the photon conductivity. Without water, the fuel cell does not work. But if you have too much water, the gas transport gets stuck, and the fuel cell, well, doesn't produce any current or heat at all. I divided my presentation in two main topics: the combination of CFD and Neutron radiography, and the combination of modeling with Monte Carlo and Synchrotron tomography. Let's look at the first one. Basically what we did is we simulated a fuel cell at particular operating conditions, and we visualized these conditions and the same fuel cell components with Neutron radiography to see where the water actually accumulates and how it is removed. The research was done in Berlin. Well, for details, you can look at the slide. All the boundary conditions are always mentioned at slides. On the slides, well, there should be questions. What did we look at? The object of investigation was a fuel cell, a single cell, with an active area of around 100 square centimeters, with meander-shaped channels in rectangular shape. Actually, it's quite the same fuel cell. If you want to know more details about the fuel cell itself, about the composition of the components, for example, you can visit us at our booth all the time. We are glad to ask questions. How is the imaging done? Basically, you make a picture of a fuel cell and you divide that by an empty fuel cell to see the actual water. So that this is done with particular operating conditions. The instrument where we did the Neutron radiography has these specific.
Hello? Cool. Well, now the microphone.
We did images with an optical resolution of, well, actually this 25 micrometer per pixel is with a small fuel cell, as we have a normal, state-of-the-art fuel cell of 100 square centimeter. We get a resolution of 69 micrometer per pixel. These were the operating conditions we were simulating and actually also experimentally investigating. We took dry gases into the fuel cell, and the question was, with current density steps at a high and a low current density, did we see water inside, and actually where can we identify the water? The simulation was done with Anders Fluent with a PEM module, and we saw specifically in the regions 1 and 2 liquid water. We did a one-phase simulation. It means a higher percentage of 100 is liquid water. We simulated only one phase due to computer and simulation results, because as more complex the simulation gets, the bigger the computer and the longer time it takes. What did we see with Neutron radiography? We see the channels of the anode, and we also identified water in regions 1 and 2. So they basically suppose those results. This is a video, well, I will press in a few seconds, just to tell you, these are the current density steps of 1.2 and 1.8 we performed. And you can see the water accumulating at low current density and moving at fast current density, moving at 0.8 current density. So what you see basically is the water does accumulate accordingly to the simulation, but turning up the flow, the water is sufficiently removed so that the fuel cell doesn't get stuck. Now, in my second part, the Monte Carlo modeling in combination with synchrotron tomography. As you saw, with Neutron radiography, we could visualize a whole cell with an active area of 100 square centimeter. And with synchrotron tomography, we can simulate smaller fuel cells, because the object of the window is quite small, but the optical and the time resolutions are higher than with Neutron radiography. That means we have a spatial resolution of 5 micrometer per pixel, and this can be directly correlated to a Monte Carlo simulation we did with the same resolution. Similar to the Neutron investigation, we have a source. We radiate an object. The image is stored on a CCD chip, and with a tomography, in contrary to radiography, we rotate the object in small angle steps, and at each step an image is taken, and afterwards they are combined in a 3-dimensional view of the fuel cell. With a small object to investigate, you can have a resolution of 0.7 micrometer per pixel, and that's really good to, especially to visualize, for example, the micropose layer of a GDL, which has a thickness of between 40 and 100 micrometer. So you need a really high resolution to see the water inside the MPL. Some results from synchrotron tomography. You could, for example, see the pathways that the water takes from the reaction layer through the GDL into the channel by, as described before, dividing the operated fuel cell by the empty fuel cell. It means this fuel cell, the GDL, was removed to see the water by this difference imaging. You can also see the water accumulation under the channel and under the rib over the different layers of the GDL. This helps to get an idea of the water transport through the MPL. It means if you, for example, have a highly hydrophobic MPL in contrast to a hydrophilic substrate, how does that influence the water transport? This is a fuel cell we were tomographing with a synchrotron beam. By looking through, you can see the channels, the fibers of the GDL, or the membrane. And this is basically how it's done, how a synchrotron tomography is done, by looking at the different layers inside the fuel cell. Well, for Monte Carlo simulation, we took those three-dimensional fuel cells, divided that in binary images of the different layers, with each a thickness of the resolution of 5 micrometer. We took a specific region, imported that in Monte Carlo, and simulated a hydrophobic region inside the fuel cell, inside this GDL, with specific conditions similar to the synchrotron tomography. And afterwards, within the fuel cell, well, for the given operation conditions and the given hydrophobicity of the GDL, we simulated where the water could accumulate. Corresponding to the surface energy of the hydrophobic and the hydrophilic material, the program decides where it's most probably accumulating the water. These are the results taken with the experiment. You can see that inside the pores of the GDL, the water accumulates, and also inside the channel. As shown before, you can also visualize the water content in the different layers of the MPL and the substrate. You can basically see that in this region where the water actually is, where the reaction takes place, the water content increases under the rib or the channel from where it is removed. You can see a similar trend between the experimental and the simulated results. This means that Monte Carlo is a good tool to change the content of a GDL. For example, if you create a difference in hydrophobicity, you can see how the water content changed and actually where it's assumed to accumulate. Now I will conclude my presentation. My presentation was to visualize the water content and to verify simulations. That means that simulation and visualization are in good correspondence, and that they some sort of interact. So a combination is really useful. We saw the water inside the channels by Neutron radiography. We saw the water inside the GDL with synchrotron tomography. And with CFD and Monte Carlo, we could simulate where water is going to be inside the fuel cell, and together with the visualization, we concluded that it the simulation itself, that the predicted water evolution is really likely, is near to the real evolution. Well, thank you very much for listening. I would be glad to ask questions, and if you have specific questions about the simulation or the radiography and tomography itself, you can come to our booth and ask me or my colleagues in person. Thank you.
Thank you very much, Mrs. Klages, for this very interesting and informative presentation. Now, the question here at the audience, do you have any remarks here right now for Mrs. Klages? Yes.
Yes, hello. Very interesting work. In terms of future work, do you have any ideas on how to relate the location of the water within the GDL catalyst layer, microdiffusion layer, to the actual performance or voltage drop or performance of the fuel cell?
Well, there are some sort of boundary conditions. If the GDL is completely filled, the fuel cell performance is quite low. But it's also, there are several investigations about how the humidity, the relative gas humidity inside the fuel cell is optimal for a good performance. So if we perform the actual experiments during Neutron and Synchrotron, radiography and tomography, we actually measure also the performance. And for example, by impedance spectroscopy, you could correlate the resistance to the humidity, for example. So if you simulate or create with CFD or Monte Carlo the experiments we performed, you can know actually where the performance is going to be. And if you, for example, perform a CFD simulation, you can also get the performance as a direct output of the simulation. Did that answer your question? Okay.
Thank you. Who's first?
Hello. I want to ask you a question about, do you have any clue about the dynamics? Because you always talk about the steady state every time you have, and then you adjust your model with the Monte Carlo simulations. But do you know something about the dynamics, how the water moves in the GDLs?
You're actually talking about the GDL or the flow field itself?
Yeah, from the GDL to the flow field, exactly.
Okay. Yeah, as I showed with Neutron radiography, you can actually see the water moving through the flow field channels. And with high resolution with Synchrotron radiography of a few micrometer per pixel, you can also see the movement from the GDL into the channel. For example, that the water accumulate and droplets are created on the surface of the GDL, and they some sort of erupt in the channel. There's some sort of eruption. We actually saw that by performing a radiography with synchrotron radiation. What I showed here is a tomography, and tomography can only be in stationary application. Well, because the fuel cell is rotated during the tomography, and that takes, let's say, around 5 hours. So you cannot see the dynamics inside the fuel cell. But if you take radiography, for example, from in-plane direction, you can see the channel and the GDL and the water coming from the GDL in the channel. So it is possible, actually.
Hello.
Hello.
Very interesting work. Thank you very much for the presentation. I got a question. So first, what are you going to do with these results then? Are you going to incorporate them in new design strategies? Are you going to, I don't know, develop more new materials? So so you show that you can simulate what you have observed during the experiment. How are you going to proceed with that?
So, for example, with the Monte Carlo modeling, an actual study is to change the PDFE content. For example, if a GDL is degraded during the operation. The PTFE content decreases, and so it gets more hydrophilic. And for example, we performed different Monte Carlo simulations at different times of degradation, let's say. And this is one study we did to change the properties actually. But you could also change, for example, the porosity. And as an input into the simulation was the actual tomography of the fibers, you can also take fibers which are thinner or thicker. We can also simulate that, yeah.
Thank you very much. So, you're here at the booth at the group exhibit Hydrogen and Fuel Cells. So, where's your booth? Can you explain it to the audience? If someone likes to visit you or to ask questions more personal or discuss the topic detailed?
Of course, everybody's free to come when you have specific questions. It's always better to answer questions in person. Well, our booth is that direction, well, almost on the other side.
Okay.
So it's a rather long way, but it's not too long, I guess.
I think so. Very, very interesting and informative presentation. Thank you very much for being here. It's your big hand now.
Thank you.
Thank you very much. Please have a seat. After a short break, we continue our program here with a presentation by the company Clear Edge Power. Thank you very much.